математического языка R внутри Postgres. И это на самом деле очень хорошая вещь, потому что вот представьте себе, сейчас последние несколько лет с помощью этого языка все стали делать любую статистику, да, то есть в академии, Data Science люди стали эту штуку использовать. Но эта штука медленная и такая не очень хорошая в смысле производительности, потому что это писали там математики для математиков, но она очень хорошая именно с точки зрения реализации математики и удобства. Всякие идеи, как ее ускорить, распараллелить, там, повесить на ходов или что-нибудь в этом роде, они очень печально выглядят. И вот Джо, собственно говоря, сделал очень большую работу по вставлению этой штуки как процедурного языка в Postgres. И вы можете, на самом деле, взять всю мощь Postgres и использовать всю мощь языка R с помощью этого. Джо давно работает с Postgres. Ну, я думаю, что он сейчас скажет пару слов о себе, и вы дальше погрузитесь в увлекательное путешествие по миру математики и баз данных. So, welcome, Joe. You can start.
Can everyone hear me? Do I need the microphone? Hear me right now?
But the microphone.
Better with microphone.
And for the video too.
Okay, this works. Hi, I'm Joe Conway. I've been working with Postgres for about 16 or 17 years, and I became an active member of the Postgres community right around 2000, 2001. PLR is something that I wrote back, I think the original version was in 2003, and so that's what I'm going to tell you about today. If I go too fast and if you want to slow me down, please let me know. If you have any questions, just interrupt and I'll try to answer them. So how many people here are familiar with the R language? A few? Okay, I assume everyone here is familiar with Postgres, that's why you're here. So the R language is specifically designed for math and statistics. And one of the interesting things about it is that it's become so popular in many of the analytical communities that the cutting edge research, the newest types of analysis that people are developing are often available as packages for R before they're available anywhere else. And because of that, you know, this was written, as I said, back in 2003, but nowadays you can connect to R from SQL Server, from Oracle, from SAS, if you've heard of that. That's kind of the old mainframe statistical package. All of those things will connect to R in order to allow you to do analysis, and the reason for that is because R is so powerful and has so many things available for it. I'm just going to take a quick sidebar here. This is the part of the main R site. It's called CRAN. So this is where the packages are available. On that page, there's a link for packages. You can see here, it says currently there's 6,845 packages available for R. So that just to give you an idea of how much there is available for R that you can use. And one of the kind of neat things they've done is because there's so many of these packages, it's hard to figure out, well, which one do you want to use for what you want to accomplish. So there's actually this thing called task views. And so these task views actually orient or organize the packages into groups according to what you want to do. So this is kind of a nice page to know about. If you want to do machine learning, you can come to this link and it has a discussion about all the various packages that are available in R to do machine learning, and so on. They've got high performance computing for doing parallelization, all kinds of other things. So this is something that's worth exploring if you're not familiar with it. So obviously everyone here knows what Postgres is. PLR is the glue between them. So just like we have PL Perl, PL Python, PLR is just a wrapper that allows you to create R functions inside of Postgres. So why would you want to do this in the first place? Well, one of the reasons is you want to be able to leverage skills of the people that you have. statistics and math tends to be kind of a specialty. It's not something that your usual web developers or your other programmers may be very good at. You might have specific people who are doing the math and statistics for you, but those people often don't know how to program with a database. They know how to program with R, typically. So by using PLR, you can let them write their analysis in R, which is a language they're familiar with, and then kind of, I don't know, later on I'll show you how to do this, but you can kind of cut and paste it into a PLR function, and now you bottled it up and put it into the database. You can leverage your hardware this way. If you've got a lot of data that you're trying to analyze, why push it off to a laptop when you've got a server that's got 16 or 32 cores and 256 gigs of RAM? You can optimize your use of bandwidth. Same argument. If you've got a lot of data that you're trying to analyze, why pull it out of the database, send it across your network, land it on someone's laptop, when you can do all the work right there? You can also ensure that you've got consistency. If you're allowing people to do their analysis kind of interactively with a language like R, it's nice in that they can do their exploration, figure out what kind of analysis they want to do, but once they're done with that, you want to ensure that this week, next week, the week after, if you feed some data to some type of analysis, you want to make sure you get the same consistent result out of it. And one way to do that is to put it into a function that now the DBA controls. You can abstract the complexity, so if, you know, some kind of analysis might be several pages of R code or any other kind of code, you'd like to be able to just bottle that up as a function and just say, give me this type of result. And that way, the guy who's writing your website, the guy who's writing the program that people are interacting with, he doesn't have to know any of that stuff. He just needs to know, I call this, I write a very simple SQL statement that's going to execute this very complex thing for me. And as I said a few minutes ago, it gives you the ability to leverage R. R itself is a huge ecosystem of things that you can access. And so by using PLR, you can get access to that. Like everything, there's cons as well as pros. There's reasons why maybe you don't want to do this. If you, from the perspective of a Postgres user, the things that you do in PLR are going to be slower than things that you can do natively in Postgres. So you wouldn't want to do standard deviation in PLR. You could certainly do it, but it's not going to be faster than the built-in standard deviation in Postgres. And R is not a trivial language to learn. It's kind of, if you're not familiar with it, it takes a while to kind of wrap your head around it, to understand how to do programming in R. It's not like a lot of other familiar languages. And it's certainly not like SQL. If you're from the perspective of an R user, there's also downsides because it's more difficult to debug your code as you're going once it's in a PLR function. So again, what you want to do is work in R interactively and then figure out how to get your analysis working, and then once it's working, then you would put it into PLR. And again, the SQL side of it for an R person is a new language to learn. In terms of creating PLR functions, they look, if you're familiar with R, this is what an R function looks like up here. It looks a little different from that, but mainly this function body that gets wrapped in the decoration here in R really is the same function body that you would use in PLR. It's just wrapped in the normal Postgres create function syntax. PLR does support either named or not unnamed arguments. So if you don't name your arguments, then inside the function body you reference them as arg1, arg2, because the R language doesn't like the dollar signs, like some of the other languages you may be familiar with, like PLP2SQL or SQL functions. But if you name your arguments, obviously you just reference them the way you write them. So in terms of very simple example of how to use, first you create the extension. It supports the normal create extension syntax. You create here's an example of a very simple function. A data frame in R, if you're not familiar with it, is basically like a relation. It's rows and columns. Columns, potentially different data types. And so this, and in this example, you can see that PLR does support set returning functions. So you can create this simple function, and it's going to return, when you call it, ABC and 1, 2, 3. So there's not enough time to go through everything that you could possibly do with PLR in just an hour. But what I'm going to try and do is highlight some of the main features for you in the rest of the time that I've got. R PostgreSQL is a library or package for R that allows you to connect to Postgres. So just like you'd want to do from other languages, you want to have some kind of ability to run a query against your database. R PostgreSQL allows you to do that from R. PLR has a specific built-in R PostgreSQL compatibility. So the same commands that you can use for R PostgreSQL to connect to Postgres will work in PLR. And so what this allows you to do is, as I talked about earlier, I can have my statistician writing in R, using his normal syntax to connect to the database to grab data, and then I can literally cut and paste that body, wrap it in, create function syntax, and create a PLR function out of it. So all of these are all the main functions. It's not literally everything in R PostgreSQL, but it's all the main stuff that allows you to connect to the database and send a query. The advantage that you get out of this in PLR is when you do this from R, it's using libpq, so it's going out to the server and making a connection. When you're doing this from PLR, it's using SPI. So SPI is just an internal connection to the database. There's no additional process. All of the data that you're accessing within the embedded R engine in Postgres is all in the same process. So in this example, this is an example of, how many people are familiar with the traveling salesman problem? Anyone? Very few. So the traveling salesman problem is, the idea is that you've got a salesman who needs to visit 50 cities, spread out around the country, and you want to find the most efficient way to go visit all of those 50 cities. And it's known as an NP-hard problem. It's not one that you can solve in a reasonable amount of time. But R has a package that will give you a good approximate answer in a reasonable amount of time. And so what this example is doing is it's solving the traveling salesman problem in, as you can see, just a few lines of code. And this is what it would look like if I'm doing it directly in R. And now you can see really nothing has changed. I just changed the part of it that makes it a function, and now it's a PLR function. And so when I call that, if I call that from R, I'm going to get an answer that looks like this, and if I call it from Postgres, I'm going to get the same answer in just a slightly different format. How many people here have ever written their own custom aggregate in Postgres? Or how many people even know you can do that? Yeah, well, that's one of the, personally, I think one of the coolest features Postgres has is the fact that you can write your own aggregate functions. So the way that works is you can have one function is required, you can have potentially two functions there's a state transition function which will get called on every row within the group. And basically it'll get passed in the value that you feed to the aggregate, along with the value from the last call. And then it will put out one value which will go to the next call within the same group. When you get to the bottom of a group, either you can return that value and that's the result of the aggregate, or you can feed that to what's called a final function. And the final function takes what's been aggregated, does some final calculation on it, and gives you back the result. So in an example of average, the state function was basically keeping track of the sum and the count, and then the final function does the division and gives you an average. So this is an example of a PLR function that implements a new aggregate. Now, until recently, this was pretty much impossible to do in Postgres. I think as of 9.5, it's the new, one of the new features in 9.5 is going to allow you to do this actually natively in Postgres. Bruce, do you know the set aggregates? That's 9.5, right?
Set aggregates.
Yeah, so that would allow you to do this actually natively in Postgres, which, as I said earlier, if you can do it natively in Postgres, you probably should because it's faster. But this example shows you how you could do this in older versions of Postgres quite easily. This quantile function is just a single line call. So quantile is going to take your data values and bin them up. So in this case, I'm saying I want bins, 4 bins. So that's why I'm going to call this thing a quartile. And by creating this one function, which is I'm going to use as my final function, and then this is just standard Postgres stuff here. I'm going to create a custom aggregate called quartile. I'm going to feed it any element. I'm going to use array append as my state function. So basically, as I march through the members of a group, I'm just going to build up an array, and then I'm going to feed that array to the quartile function as a final function, and that is going to give me back my final result. And so this call here, this is actually based on some real data that I collected from a place where I worked years ago. It's been anonymized somewhat, but this is real manufacturing data. And looking at it this way is interesting, but one of the things R lets you do is some nice graphics as well. This is called a box and whisker plot. So by doing that aggregate, what I can see is that this manufacturing station is producing different results than that one. So I need to go fix something. Window functions. Anyone familiar with or ever use window functions? A few? Again, one of the pretty cool features of Postgres.
Maybe they're called for others know them analytical functions. I think Oracle both know them as analytical functions, I suppose.
Okay. So window function is similar to an aggregate and also different. Basically what you're doing is you're working on groups of data, but you've got a window. I think I've got a graphic for this too. What you have here is the data gets broken up. The groups are called partitions. And then within a partition you have this sliding frame that will march down the rows. And whatever row you're currently on, unlike an aggregate, you'll get a value for every row that you feed in. So in an aggregate, you've got, if you have 50 members in a group, you get one result. But in a window function, you're going to get a result for every member in the group. But you've got access to all the data in the frame for doing calculations. And PLR does support window functions. I think the only other procedural language in Postgres that supports window functions that I'm aware of is PLV8. Does anyone know of any others? Bruce, do you know of any others? So this example is a bit too complicated to go through in great gory detail, but what I'm doing here is I'm just creating some random data that simulates earnings in stock price data. And so what this function is going to do is it's going to look to see whether I can predict earnings this year based on last year's earnings by doing a simple regression. So I'm essentially fitting a line through the data. And the way I'm going to do that is with this fairly ugly window function. But so you can see that for each year I've got the earnings per share, and then this lag earnings per share is just giving me the value from the previous year. And then I wrote the function. You don't want to do a regression if you don't have enough data to have a meaningful line. So it's set up here to not even try unless it has at least 9 rows. So that's why you don't have data here until we get down to this point. So the slope is basically going to give me my relationship between last year's earnings per share and this year's earnings per share. Any questions on all that before I get into? I've got several examples that I'll go through in a little bit more detail.
Why aggregates are slower than R? So what is the biggest kind of slowdown? So bottleneck there. So why are they slower than
the native?
Than the native ones?
Well, R is a very powerful language, but it's not necessarily the fastest for doing calculations. And you know, it's a lot of overhead, right? So the native stuff that's built into Postgres is all written in C. It's linked right into the back end that you're running. Whereas the stuff that you're doing in R is, you know, it's interpreted.
Okay.
So it's just naturally not going to be as fast. Any other questions? Okay, so here's an example of stock price data. I'm going to get the high-low close data from Yahoo for a stock symbol. I'm going to plot it with Bollinger Bands and this does require some extra packages. These examples are all written so that hopefully you should be able to just cut and paste them if you want to try them yourself. I'm assuming the conference will make the slides available on the conference website. Is that the case?
I don't know.
If not,
if they're not planning to do, we will force them to do.
Yeah. If nothing else, these same slides will be available on my own website, so joeconway.com. But you should be able to play with this by cutting and pasting. The examples are fairly complete. So this is the command in R if you need to install some of these packages, these external packages. You say install packages, and then this C just basically makes this into a vector, and then these are the packages that I want to install for this example: XDS, defaults, QuantMod, Cairo device, and RGTK2. So these last two, Cairo device and RGTK2, allow you to print your graphic to memory and capture it as the image. Because R normally will just produce like a PNG or a JPEG file, but it writes it out as a file to disk. And so in these examples, I'm going to show you how you can actually just capture it in memory and return it back to Postgres. So in this function, these first three calls here are just loading the libraries that I need. QuantMod is the library that's going to do all the heavy lifting in terms of the analytics here. These first two lines are setting up a device in memory, which is what I'm going to plot to. So my chart is actually going to get sent to that. This one call here, get symbols, goes out to Yahoo, and I think it works with several other services that have stock data, but it'll go out onto the internet, grab the stock data, and bring it down and put it into basically a data frame that I can use for analysis. chart series is coming from this quant mod library as well, and that's going to take the data the high-low close data that I downloaded, and it's going to produce a chart for me, which you'll see in a second. And then these two lines here are now going to take that chart that was plotted to the device in memory and store it in a buffer for me that I can return to Postgres. And you can see I've identified this thing as returning type by day. So if I want to return an image, I'm going to return by day from my PLR function. I'm going to get the actual image. In general, one of the things I didn't really cover, but with PLR, if you are either taking an argument that's a by day, or if you're returning a by day, it's treated a little bit specially. It's treated as if it were an R object. So in this case, since I'm returning by day, I'm going to return basically the R object that represents that image. But you can do other useful things with this. You can, as I said before, a data frame is kind of like a table. You might have to do quite a bit of work to get the data into your data frame that you then want to do several different types of analysis with. Well, in that case, you can actually return that data frame as by day, which keeps it as an R object, store it in a table in Postgres, and then write other PLR functions that accept that field from a table as an argument, and then finishes the work that you want. So if you've got some kind of analytics that take a lot of time to get that table, and then some kind of final, you can think of it almost like a final function and a state function. If you do all this work to kind of get the data in the data frame, store it in a table, and then you can feed that to another function later and use that to do your final calculation quickly.
Is it serialized in R format, or is it just a table stored as a table? So it's
when you return the by day, it's basically the R format gets serialized, and then that just gets stored as a blob.
As a blob.
So one of the things, if you're doing this, if you're doing the charting with PLR, often your server may be headless, right? You don't. And one of the things that R needs to do, or at least it used to, I think this may have changed recently, but it used to need X windows in order to do the plotting. So if you have a headless server and you need X windows, you can get the same functionality using a virtual frame buffer. So this will just show you how you can set that up so that you're able to create the graphic on a headless server. This little bit of code is just some PHP code. I'm going to connect to the database. The query, select PLR get raw, PLR stock data. So this function we just saw was PLR stock data. As I said, that I'm going to feed it an argument which is a stock symbol. It's going to return the actual R object which represents that chart. And then PLR get raw, it strips off kind of the R, a few bytes that R wraps around the object, which is the image. And then I'm just going to take it, I have to convert it from hex back to binary, and then I'm just going to send it to the browser. So having done all that, this is what I get. So I think that's really quite amazing that you can take about less than a dozen lines of PLR code and less than a dozen lines of PHP code, and you can get that. Any questions about that?
So what you return from there is really the image. So it's kind of this thing that you return.
In this particular case, the function that I wrote returns the image wrapped with a little bit. That's why I needed the PLR get raw is provided so that you can strip that off so it really is just an image. Obviously, if you were returning a data frame, you wouldn't want to strip that off. You would just store it the way it is. and then pass it back in, and then when you pass it back in, R just knows that it's a data point. So this is an example of something called Benford's law. Is anyone familiar with Benford's law? Not a single person. Okay. Benford's law, this guy, not all that long ago really, I think it was kind of in the, I think it was in the 70s or early 80s, figured out that if you take a set of data that is of the type where it kind of has a natural geometric progression, which is a lot of data. Sales data, cost data is often geometric in nature. When you analyze just the first digits or the first two digits of the numbers in that data set, they actually have a predictable proportion of ones versus twos versus threes versus fours. Basically, ones are more common, the most common, and as you go down, they become less common. So nines are the least common digit. And the same thing goes if you want to analyze it for 2 digits or 3 digits or more even. So what you can do with this is that often when people fake data, they don't realize that this law exists, and so they don't make their data look like it should look in order to pass this law. So you can use this for fraud detection. It's not like a guarantee. If something doesn't meet the dispersion that you would expect, it doesn't guarantee that fraud is involved, but it at least gives you an alert that you should check it out.
Because you can analyze the numbers from the elections.
Yeah. You'd have to do some research to see whether that really should follow Benford's law, but there is a, I give you a link here on Wikipedia for some information about Benford's law. It can be used for analyzing sales figures, census data, medical, expense reports, and the example that I've got here is energy savings. There's actually a program, I'm from California, there was a program in California for getting rebates for doing some kind of energy savings. And it's all, the data was all public, so I decided I would take a look and see if at least at first blush it looked like there was any problems, any fraud going on with people getting their rebates. So, you know, as I said earlier, trying to keep this as complete as possible so you can try it out if you want. This is the table that I used, and then you can download this CSV file from this link here. In this case, I'm creating a type to return. So this is one way that you can have a set returning function that returns rows and columns without having to specify all the columns every time you call it. This is nothing specific to PLR. This is just Postgres set returning functions. The calculation, you know, you can look this up. It's on the Wikipedia page what the calculation is. But what it's looking for is basically something called distortion. And a factor which is an indicator of how statistically significant the differences are. So in this case, when I ran through the numbers from the data that I got, it actually was not very much distortion and not very much significance. So it appeared that, at least that using this as a method, that there was no fraud going on in this case. Okay, so now I'm going to go back to that traveling salesman problem that I showed you a little bit earlier. This problem, it turns out, has a lot of use cases. It's, you know, if you think about it, if you've got trucks, you want to have the most efficient route that are making deliveries because you want to save gas, you want to save time. If you have land management issues, when I first worked through this example, I was working with a guy who does Actually, his degree was in forest informatics. I never heard of that before. But when you're managing trees that are going to get harvested, there's actually a lot of analytics that goes on because you want to maximize the yield and the output of those trees. And so they will send people out into the forest to specific locations to take measurements. And if you're the guy who has to go out into the forest and take those measurements, which this guy used to do, you want to do that as efficiently as possible because you'd like to get back before it gets dark. Semiconductors. I used to work for a company that named Cymer that makes lasers that are used in semiconductor lithography. And when you make computer chips, they're basically, you take a wafer of silicon that's 12 inches or 300 millimeters, and you shine a light through a mask after you've put some chemicals on it, and it draws the pattern of the circuit right on the silicon. And then you do an acid etch, and you just do this repeatedly. But what you end up with is this wafer that's got maybe 1,000 individual chips. And in these factories, each one of those chips might be worth $100 US. So what's that in rubles, roughly 50 times?
Everybody knows, yeah, what is $100 US.
So each one of those chips is worth $100 US, and there may be 1,000 of them on one wafer. So you're talking about $100,000 per wafer, and the equipment pumps like 60 wafers an hour through. So factories that make chips are basically money-making machines. And every second is literally tracked in these machines. So if you're doing inspection of those chips for quality control, you want to sample them, but you want to visit those samples as efficiently as possible because you want that thing to be done quickly. So this example is quite long, again, just in the interest of keeping it complete enough that you can do cut and paste. It also combines PostGIS spatial data with PLR, which is kind of an interesting use case. So I'm not going to try and go through this in gory detail, but basically here's creating the table, adding some geometry columns, creating some indexes, populating it with some data. So this is basically the table that holds all my locations that I'm going to go visit. And then I'm going to create a table for my output. One of the other features of PLR that I didn't really go into is something called PLR modules table. That was an idea that I stole from PL Tickle, but I don't know how many people here know Jan Vik, but I told Jan that I stole his idea. Basically, because R is an interpreted language, when the interpreter first is brought into your process, your Postgres process, the init function will look and see if this table exists. And if this table exists in exactly this form, it will take this mod source field and compile it, which now makes it available in the R environment that you've got. So what you can do is use that to kind of preload R functions that you've written yourself that are now available to be called by your PLR functions. So this is the same code we looked at before. There's a SQL statement that's going to pull the location data out of the table and then solve the traveling salesman problem and return the route, basically. Now there's some helper functions that are needed to do that I've created, and that's what these next couple of slides are. So this function is what is going to actually make the route that I'm going to plot. And then here's where I'm inserting into the PLR modules table these helper functions that I created. And so when you run it, it's going to give you back, the order that you should visit these locations and what the distances are and what the bearings are to the next one and so on and so forth. But it's probably better to look at it this way. So you can see here, these are the places that I wanted to visit, and it came up with what, you know, at least visually looks like a pretty good solution. Any questions about that? There are packages available for R that will let you load in maps for various parts of the world. So you can plot the lat long basically on top of the map. There's a lot of spatial data functionality that's available for R. That's one of the reasons why it's very interesting to be able to use the PostGIS in combination with PLR, because then you can make use of all of that functionality from R. So in this example, this is a real example actually. There was a guy at a university in the US who was doing analysis of seismic events, so earthquakes. And he was having a performance problem with PLR, which I then fixed for him. But when they collect the data for an earthquake, you know, earthquake lasts maybe 15, 20 seconds typically. And what they collect is a bunch of floating point values that indicate what the waveform of the earthquake looks like. There's about 16,000 elements, it looked, at least in a typical one that he was analyzing. And so in this example, I'm going to load 1,000 seismic events in a table. And here I'm doing it using PGSQL. So I'm just pulling the data out of the CSV file repeatedly, and it takes 37 seconds. I rewrote that to load the data using R, basically. So loading it into R objects and storing the R object in a table. And it took 12 seconds. So here's a case where it was actually faster to do it using PLR than it was using the native Postgres functionality. So now this function is going to just plot the waveform for me. So you've seen this before. I'm using the same libraries, the Cairo device, the RGTK2. Actually, I don't need that quant mod there. I should take that out. So I'm setting up the device to plot to, and in this case, when I bring that data in, I've just brought it in as basically a vector. So it's a vector of floating point values. They represent just the waveform. And I just simply have to plot it. And so that's what this particular earthquake looked like. But what's more interesting is, with R, again, you've got all this functionality available to you. Wouldn't you really like to know how to use that waveform to design your buildings so that they don't fall down? How many people here are familiar with the idea of harmonic frequency? A few? So the idea is that when you take a structure, you can calculate what its harmonic frequency is. If you vibrate a structure at or close to its harmonic frequency, you get amplifying effects. So what you don't want to do is design your building so that its harmonic frequency, or bridge or anything else, so that its harmonic frequency is close to the harmonic frequency of an earthquake. Because if you do, then it amplifies and the building falls down. And there's this famous video that they show to all engineering students in the US at least about a bridge in, I think, Seattle or somewhere in Washington State in the US. It was called the Tacoma National Bridge. But it was designed years ago, and they didn't take this kind of thing into account. And there was this big storm that came along, and it moved the bridge right at its harmonic frequency, and the whole bridge just collapses. So what this code is going to do is it's taking that waveform and it's using a fast Fourier transform to find out where all the energy is in the frequencies that are involved in this earthquake. So this code here is looking at, this is where it's basically doing the fast Fourier transform. And now when I plot it, I get this. And what this is showing me, this is basically frequency of the vibrations. And the height here is the amplitude, or the amount of energy at that frequency. So now I can actually do the calculation. I can see this is the frequency with all the energy. I wouldn't want to design something with a harmonic frequency that's close to that. Okay, any questions on that one? I've got one more example. I'm almost out of time. How much time do I have?
How much? 45 minutes. So
Theoretically, I'm out. Okay.
theoretically,
Well, I'll go through this one quickly. This is an example of statistical process control. This is something that was developed back in the 40s for doing, helping people analyze when they're manufacturing. And since I'm out of time, I'm going to go through this pretty quickly, but I've got a link up here for the SQL code that is involved in this. And the result, again, I'm going to use the PLR functions that I wrote to produce these charts. So an X-bar chart is showing you whether, with these control limits, this is the average of the process. These are the natural control limits of the process, and when you have data that falls outside of that control limit, it's an indication that something has gone wrong, or something has changed at least. So the same thing for a range chart, which is you're taking samples of data and you're looking at how much variability there is in there. So if the variability suddenly changes and goes up, that's also an indication that something has gone wrong. And then finally, this is a geometric moving average. So all the code for that is available in that link. And that's it. Any questions?
I have one. Just a remark, probably. Well, thank you very much for the very interesting lecture.
Thank you.
And the first thing I thought when I read the title of your lecture was the next one. Actually, I don't know what's going on at CERN. I mean, Big Hadron Collider. I just know that they are using a library, C library, called ROOT, R-O-O-T, for some statistical calculations.
Mm-hmm.
And I understand that it's not a language like R, it's just a library. But perhaps we could use, this is open source library, so perhaps we could use some classes or something from this library to speed our calculation up more.
Yeah, that's interesting. There's another library out there called Madlib, which is, I think, written by the same people who, Pivotal, who do Greenplum. I'm not sure if you're familiar with the Greenplum database, but that was built on top of Postgres. And they've got their own C library that does specific statistical calculations, and it's written in C. So similar thing. I've thought about the fact that I could potentially include some of those capabilities in PLR. So at some point, if I get time, I might look into that.
Yeah, because in CERN they have a monster amount of data.
Oh yes, I'm sure.
To analyze. Okay,
Thanks.
thank you.
Thank you. Any other questions? Okay, thank you.